All right, so I'm going to show you something pretty amazing here, totally optional, but um, during quarantine, I've been reading a little bit more, and I've even found some time to read some stuff on calculus. I got this book at Christmas, Change is the Only Constant, The Wisdom of Calculus in a Madcap World. Pretty interesting if you uh, want to pick it up at some point. Some fun drawings and lots of fun connections with things that we have done in this class. And I learned something new the other day as I was reading it, and it actually ties in nicely with improper integrals, which is what we just talked about. And so here's a fairly straightforward improper integral. And so e to the negative x from 0 to infinity. The antiderivative just has to put that negative out in front. We take the limit. E to a negative big power is 0, and so I end up with just e to the 0, which is 1. Okay, so that's sort of nice, nice simple answer from this improper integral. And now I'm just going to put a constant in there. And so I put an a in front of the x. So when I take the antiderivative, I have to correct for that. So I get a 1 over a out in front now instead of just a negative 1. When I take the limit, this power of e still goes away. And e to the 0 is still 1. And so I just end up with 1 over a. And so as a gets bigger, the function's going to decrease faster and it's going to make the area smaller, basically. If a gets smaller, if it's like 1/2 or 1/10, the area will get bigger. So why is this so amazing? Well, here's this sort of chain of events. And this I'd never heard of before, but it's sort of a cool idea. And so I've got this improper integral that we just figured out. And so now I'm going to take the derivative of both sides of these things, but I'm going to take the derivative assuming that a was the variable. And I'm just going to sort of take the derivative of the inside here, and I guess we won't get too bogged down in whether we can do this and why we can do this, but it does end up working. So the derivative of this, if a is the variable, is I still get that exponential back, but now the derivative of the inside is negative x, right? Because a is the variable, and negative x is like the constant, so we get that. 1 over a is a to the negative 1. And the derivative of a to the negative 1 will be negative a to the negative 2, which is negative 1 over a squared. Okay, well, so big deal. But now we're just going to keep doing this. And so I'm going to take the derivative of this again with respect to a. And so the 2 comes down, the negative 2 comes down, and so I get 2 over a cubed, right? A to the negative third. Here, again, the exponential stays the same. And then the derivative of the exponent is negative x, but negative x times negative x is x squared. So the negative goes away. Might be a little hard to see where this is going, but the payoff will be worth it, believe me. And so now the derivative of 2 over a cubed, that's 2 times a to the negative third. And so that negative 3 comes down and I get negative 6. New power is negative 4. And over here you sort of see the pattern. The negative comes back in, and the power has gone up on x again because I multiplied by x. And so now is sort of the big leap. And so as I continue doing this, the left side's sort of easy. The power of x just keeps going up by 1. We sort of flip back and forth between positives and negatives. Not a big deal. On the right side, if you think about doing the next one, think about what's going to happen. That 4 is going to come down, and now we're going to have 6 times 4, which is 24. Why is that so interesting? Well, because think about where all these numbers come from. I just keep multiplying by that next number. And again, the sign flips back and forth between positive and negative. But really what this coefficient in front is creating is factorial. And so that 6 was really 3 factorial. And the next one down the line is going to be 4 factorial, and so forth. And so the grand conclusion here is that this integral is on the left. I stopped writing this here, but this is all from 0 to infinity. We just get this power of x to the nth. On the right side, we get n factorial and then a with a 1 higher power on the bottom. Both sides are either positive or negative, so I can really sort of ignore that. And the amazing conclusion comes when we say, oh, well, okay, so this is true. What if a equals 1? Well, if a equals 1, the right side, that denominator goes away. I can cancel out the negatives because it was on both sides. And I get this amazing integral, improper integral. And notice what it's equal to. It's simply equal to n factorial. Why is this so amazing? Well, it's amazing because this improper integral can be evaluated one way or another, whether n is an integer or not. And so you've always wondered, right, if you try and type in something like 7.26 factorial on your calculator, it will, of course, give you, let me see, I think I've got it here. It will give you a domain error, right? Factorial doesn't make sense when we're not dealing with an integer. But when I'm doing this equivalent formula of an improper integral, we can do it just fine. And so I'm going to switch over to Wolfram Alpha here. And Wolfram Alpha is smart enough to extend it to these other functions. It does the improper integral. It uses a series representation, and it's able to figure out the answer is 8,549.92. I assume the decimal keeps going. And of course, as you would sort of hope, let's pull up my calculator again. This is, of course, in between 7 factorial and 8 factorial, as you would expect it to be. And a little closer to 7 factorial. So truly an amazing thing. This improper integral equal to factorial, which you wouldn't really expect. And even better, it allows us to extend factorial to decimals. Fun stuff.